Hello. Today is this is our lecture three, and lecture three of module one. Today I'm going to in this lecture I'm going to give you cover some topics that are beyond Poisson and logistic regression. And so these methods are extension of Poisson and the logistic regression model. So I'm going to start with brief review over disposed counter data we have covered last lecture. As a transition, go to negative binomial regression. Then I will focus on multi-category models. One is multinomial logistic regression. The other is ordinal logistic regression. Just as a brief summary, logistic regression we have learned from lecture one is for binary outcomes. And the Poisson regression we have learned last lecture is for count outcomes. When these models do not adequately fit the data, one situation is where we see the counter data exhibit over disposed. So if the data are over disposed, there are several other methods are available. One is a quasi-Poisson model we have learned last lecture. And today I'm going to cover negative binomial regression. And there are some other methods. If quasi-Poisson and negative binomial regression are still not appropriate, I will leave these other methods for your own study in the future when you has the need to learn that. Then I will move on to, we will spend more time about talking about outcomes. When you have outcomes with more than two categories, and there are two situations. One is no ordering. When there's no ordering, we can use multinomial logistic model. When the outcomes are order category, then we should use ordinal logistic models. These two models are not the same. Okay, let's first give a brief review over disposed counter data. And we now know Poisson property is the mean and the variance are equal. And in regression setting, Poisson regression is only valid if counter data have the mean and the variance are the same. However, often counter data exhibit over-dispersion, which is the mean is larger than, which is the variance is larger than the mean. And in this case, we already know from the last lecture that using ordinary Poisson models for over-disposed counter data will lead to standard errors that are too small that will affect our inference. So a next question is, how do we know? How do we know the data are over-disposed? Now we can estimate the dispersion parameter phi. We can estimate the phi by the ratio of Pearson chi-square to degrees of freedom or residual deviance to degrees of freedom. And if this estimate is around 1, Poisson regression is fine. If this estimate is much larger than 1, this suggests that the Poisson regression did not provide an adequate fit of our counter data. And we need to consider other methods to account for over-dispersion. And one method is quasi-Poisson model that could provide appropriate inference when the over-dispersion is modest. And today, we're going to learn another method, which is negative binomial regression. And as we can see that negative binomial regression is naturally accounts for overdispersion. We will see this in a minute. So what is the difference? What are some differences between for negative binomial regression compared to Poisson regression? And actually, it's quite interesting is that the negative binomial regression has the same mean structure as Poisson. So if the Poisson mean is mu sub I, negative binomial regression also mu sub I, so the mean structure are the same. They also use the same log link function. So this is the, as we're familiar with, this is the Poisson model, Poisson regression. This is the Poisson regression, and the second one is the Poisson regression with exposure. And the negative binomial model also uses the log link function. So what's the difference? Difference is negative binomial model has the additional dispersion parameter. The variance of negative binomial distribution is mu sub I plus additional term. Additional term described estimated by K. Now, K is restricted to be positive. So K is called the dispersion parameter in negative binomial model. So please note that this is a dispersion parameter in negative binomial model is not the same as the dispersion parameter we call in Poisson regression. So here is the K. Clearly, K close to 0, the negative binomial regression model is the Poisson model. Now, if K is larger than 0, then this let the negative binomial regression to account for overdispersion because it will estimate a K. It will allow variance is larger than the mean. So the variance of the negative binomial distribution is always greater than the variance of a Poisson distribution if they have the same mean. So as you can see, the negative binomial regression will naturally is natural choice when your data is overdispersed. Now I have to make note that negative binomial negative binomial distribution cannot model underdispersed counter data. That is because this model restricts the K to be positive. So the variance is always greater than the mean. Okay, so the interpretation of coefficients in negative binomial regression is exactly the same as Poisson regression because the link function is the same, the mean structure is the same. So only difference is the standard errors are adjusted for overdispersion. So that makes our job very easy. Right? So, however, I need to tell you that the SAS program amount for negative binomial model reports estimate for this K. That's the case here. And our package is use different package called glim.nb. That also provides estimate, but it is provide estimate of 1 over K. It's not K, it's 1 over K. Okay, so here just briefly SAS code. It's easy, right? So just change distribution Poisson to distribution negative binomial, or simply just NB. Right? So you just replace previous distribution equal Poisson by distribution equal negative binomial model. Everything else are the same. You can also add the D scale or P scale to further adjust the standard errors. You just add the D scale. Right? Now, R is using different package. You need to library math, then get glm.nb. Now, what R is, this is different from previous model syntax for Poisson model. You need to move offset to the model statement. Now, previously, offset is here, outside the model statement. So now here you need to move offset within this model formulation. Then everything else is just get a summary. Now, as I said, this package parameterizes the model differently. It outputs the dispersion parameter, which is 1 over k instead of k. So you need to calculate this dispersion parameter by simply just take the reciprocal of this dispersion parameter output. So I will show you this in a minute. So let's just walk through this. Now we have 3 models. We have ordinary Poisson model, we have quasi-Poisson model, and today we learn negative binomial models. And let's take a look at the example, which is we did this in our previous exercise problem. That's COVID incidence cases. And in the exercise problem you did last week is you've obtained ordinary results from using ordinary Poisson model and the quasi-Poisson model. These are the 2 results you have already obtained in the last week Thursday exercise. So here just to highlight some of the results. Elevation in terms of per 1,000 meters, in the scale of 1,000 meters. So beta estimate, this is the log rate, okay, the log mean rate is negative 0.27 in the standard error, and the rate ratio is just to take the exponentiate of beta, you get the rate ratio. And then the second variable, the other variable is the number of persons in the household. In the household, you have this log mean estimate and standard error and the rate ratio. And AIC is this value. And the quasi-Poisson model, remember the estimates are unchanged. So these estimates remain the same as the standard Poisson model. The standard error is now scale up by multiplying square root of dispersion parameter, which is this one. So when you take a square root, this is called the scale parameter. So the new standard error is just the previous standard error multiplied by the scale parameter. So you get the new standard error. With regression coefficient estimates remain the same. And the AIC is not available. That's because AIC is calculated from the likelihood function. And the quasi-Poisson model, quasi-Poisson is not a true likelihood. It's not a likelihood-based method. So AIC will not be available. This is the results from negative binomial model. Now you will have the exercise this Thursday. I will ask you to reproduce these results. These are the results from negative binomial model I've got. The beta estimate is this negative 0.42, so which is not the same as the previous from Poisson model. The standard error is similar as quasi-Poisson, and then rate ratio is 0.65. And the other variable, number of persons in the household, beta estimate also is not the same compared to the previous Poisson model. And the standard error is slightly larger, and the rate ratio is 4. And the dispersion parameter K, that's the K is for negative binomial model is 0.56, which is greater than 0. This indicates that the data is over dispersion, right? If K equals 0, negative binomial model is close to the Poisson model. Now K is greater than 0. So this also indicated that the standard Poisson model is not appropriate. AIC is greatly reduced from previous AIC. We know that the smaller AIC, the model is better. What is our output? So our output is this using glean.nb. You get, I've got this output, and the regression coefficients is similar as SAS output. These are the same, and standard error also similar. And as I mentioned in previous slides, dispersion parameter for negative binomial model is estimated is 1 over k, and not k. So calculate k by itself, we just do 1 over this value. So now you match. So the R results and the SAS results are matching. Okay, now the question is, which model should we use, right? We have a Poisson model, we have a quasi-Poisson model, we have a negative binomial model. And clearly in this, we know that in this case, Poisson model is not appropriate because the dispersion parameter is much larger. It's much larger, 520, right? 520, much larger. So we should use some other methods. Now, quasi-Poisson model, we know that the regression coefficients remain the same and the standard errors are adjusted. We also know that the quasi-Poisson is not likelihood-based approach. So this is the property of this method. And the AIC cannot be used for preparing Poisson model and a quasi-Poisson. Right? Negative binomial model explicitly tell you the variance. That's mu sub I plus k multiplied mu sub I squared, right? So this is also likelihood-based approach. Then we can use the AIC to compare the ordinary Poisson model and negative binomial regression, when the data are the same. So we usually always favor the model with lower AIC, but this is not always the case. So but generally we favor the model with lower AIC. So back to our example, which model should we use? So there are two indications in this example. First of all, k larger than 0, indicating that standard Poisson model is not appropriate when the data is overdispersed. Then second, we compare AIC. AIC is substantially smaller in the negative binomial regression than in the Poisson regression. This also indicates that negative binomial regression is more appropriate for this data. So in this case, I would choose negative binomial regression as my model and report the results from negative binomial regression because the AIC is substantially reduced. Okay, just summarize a brief summary for our models for count data. So now we know Poisson model, negative binomial model, that are two models often used for model counts and rates. And we also know negative binomial models are more flexible because it allows variance larger than mean. And there are some situations neither Poisson model nor negative binomial model fits adequately count data. When counts have excess zeros. Excess zeros mean more than would be expected on the Poisson model or negative binomial distribution. So in this case, there are some other methods available. For example, zero-inflated Poisson, zero-inflated negative binomial models that can be used for fitting the data with overdispersion due to excess zeros. Right? This is sometimes, for example, if you collect the data, the outcome is the number of comorbidities. And we know many people have no comorbidity. So your data may have a lot of zeros in this outcome. So in this case, if negative binomial model, if the Poisson model shows overdispersion and the negative binomial model also shows explosion, then you might try zero inflated models. The other model, another model, candidate model is hurdle models. So I will leave these these methods to you for your own study in the future if you have the need to learn these methods. So this is about methods for count data, for counts and rates, which include Poisson model, quasi-Poisson model, negative binomial models, and so these are the common model you can consider to use, and other models, zero inflated model and hurdle models are also available in the statistical literature and so available for use. Okay, now we're going to spend more times on logistic regression, extension of binary logistic regression to the outcomes with more than two categories. More than two categories. So before I'm go to this detail, since we cover logistic regression model in the first lecture, I thought we should go back to give some review. So let's review the setting where we use binary logistic regression. So binary logistic regression in the setting is where there is a sample of n independent trials. So we call the trials is n independent subjects, right? So in our logistic, so these are the data points you have, each of which can have only two possible outcomes, success or failure. And the probability of a success at each trial is assumed to be pi, and hence the probability of failure is 1 minus pi. Sample data look like this, n1 successes and n2 failures. N1 plus n2 is the sample size. And we know that the estimate of this probability of success is the ratio of just the proportion of data points where n1 successes. And the probability of failure is just 1 minus pi, 1 minus the probability of success. We just, in this case, just n2 divided by the total sample size. And we know that we only need to estimate the pi because the other probability is just 1 minus pi when there are only two possible outcomes. And in binary logistic regression, we're just using logit. Right? We're just using logit pi, which is log odds. Odds of probability of success to probability of failure. Then we link these log odds to covariates. So that's our logistic regression model. Now, let's extend this approach to the situation where there are more than two outcomes. Right? There are more than two categories outcomes. So let's illustrating this with three categories with no ordering. For example, beef, seafood, pork, no ordering. Still, we have a sample of n independent trials. However, each of which can have three possible outcome categories. Let's just call 1, 2, 3. No ordering, just the label 1, 2, 3. So you can think of this as beef, pork, and seafood. The probabilities of these three outcome categories at each trial are pi 1, pi 2, pi 3. pi 3 is 1 minus pi 1 pi minus pi 2. Sample data look like this. So you have the responses to these three categories are N1, N2, N3. Right? You can also thinking about the number of events. Number of events belong to each of the three categories. So N1 events in category 1, N2 events, outcome events in category 3. Number of all these number of events adding is the number of subjects in the sample. And clearly, so the probability of category 1 is estimated by N1 divided by N. The probability of category 2 is N2 divided by N. The last probability, the probability of category 3 is N3 divided by N, which is also equal 1 minus pi 1 pi 2 minus pi 2. So in this case, we only need to estimate pi 1 and pi 2 because pi 3 is just 1 minus pi 1 minus pi 2. And in multinomial regression, the idea is we only need to estimate two logits. Two logits is pi 1 log odds of pi 1 to pi 3, and log odds of pi 2 to pi 3. So you see the analogous of binary logistic regression and multinomial response data is you have a log odds success to failure. You here have a log odds because you have three categories. So is log odds of 1 to 3 and log odds 2 to 3. Basically, you compare 1 versus 3 and 2 versus 3. You need to have one group, one category as the reference group. Here, without the loss of generality, we're just using the last one as a reference group. Of course, you can use 2 as the reference group. If you have 2 as the reference group, 2 logits is 1 versus 2, 3 versus 2. With 3 categories, you only need to estimate 2 logits. The number of logits you need to estimate is C minus 1, because the last one is the reference group. Like here is the reference group. Okay, if we understand this, now we can move on to what is multinomial logistic regression. So multinomial logistic regression is applied for response outcome with more than 2 categories that are not ordered. Okay, so we are talking about not ordered. When they are ordered, that will be next section. So here we're talking about the not order, no ordering. So this is the setting. Y has, let's say, have C categories with no ordering. These categories are nominal. Beef, pork, seafood. These are the nominal. We need to choose a reference category. Let's say the last category, C, is our reference category. Now we need to fit C minus 1 logistic regression models separately. Basically, separate model. Why C minus 1, as I just said, is because you have C categories, then you have J from 1 to C minus, so you need to compare J equal 1, the first category to the last one, the second category to the last one, all the way to C minus 1 category to the last one. So you have C minus 1 logistic regression model in this setting. So this is the log. So this is the log odds of being in category J versus in the reference category C. And we can simply denote this is a logit pi sub j, j from 1 to C minus 1. So this is basically, this is total number of logistic regression model is C minus 1, C minus 1. And how many parameters we need to estimate? This is, see, I'm using J. Intercept and slope estimates are separate for each logit model. So these are a set of regression parameters for category J compared to the reference C. So how many sets of these parameters C minus 1? For example, if you compare log pi 1 to pi C, then you have their own regression coefficients, intercept and slope. Move on the second logit model, pi 2 compared to pi C, you have another set of regression coefficients. So regression coefficients are modeled to be different for different logits. What does that mean? Meaning that predicted variables have different association, allow for different association for different logits. So this is the beta, alpha and beta allow different with different logits. And clearly we know that previous logistic regression for binary outcome is a special case where there are only C equal 2. So the then interpretation is similar as a logistic regression model. Is beta j is just the log odds ratio. Log odds ratio of is the log in terms of log odds ratio of outcome category J compared to category C for each 1 unit increase in X. Right? So this, I'm here just for simplicity, just to consider as you only have one covariate in the model, for example, age. And this is just beta j. So for age, this is beta j, the log probability of log odds of probability of being in category J to the probability of being in category C is a function of age covariate. And take exponential of this beta is the odds ratio of category J versus category C for each 1 unit increase in X. So this is, so the key is you need to use in the same reference group to be compared with. So you have C minus 1 logistic regression model with the same reference group to be compared with. So the next question is, how do we choose which category as a reference category? So commonly we use common category or clinically meaningful category. For example, like smoking, right? So if you want to model probability of non-smoking, probability of former smoking, probability of current smoking, right? Current smoking. Now, for this is not you don't have to model have this category. Maybe no ordering, right? Is the former smoking not necessarily between non-smoking and the current smoking, not necessary. So you may want to just model this as nominal. So in this case, it makes sense to use non-smoking as the reference group. So in this case, you have 2 logits, non-smoking compared to former smoking compared to non-smoking, 1 logit model, then current smoking versus non-smoking as a second logit model. Right? So as you can see, there is a C-1 comparison. So there will be many regression coefficients. Think about it. If your model have 10 covariates, Then each logit model has its own intercept, own regression coefficients. You have a lot of regression coefficients to be estimated. So this is an issue. This is a problem. It's an issue. So this will increase the complexity in interpretation, right? So if, say, for example, if you have 5 categories in your outcome, then you have 4 logits. Think about your table. Your table is very large. You have 10 variables, independent variables, then have intercept. So you have a lot of the parameters you need to estimate. Think about if you write a paper, you submit it to the journal. That's a lot, right? So that's so sample size definitely need to be large. You need a large sample size in order to afford this multi-normal logistic regression model. So if you have like 5 categories as outcome, you might also want to combine to no more than 4 or 3, right? No more than 3 or 4. So that's the multi-normal logistic regression. Now, how do we estimate this? So it's SAS code is, so here I just give you an example. So for example, if you are interested about the outcome is selection of major among college students. A major can have STEM, medicine, law, others. So your model is just, this is using proglogistic model. For example, you want to understand whether sex is associated with the prevalence of major selection. And so in this case, your sex is your independent variable, and your selection is your outcome variable with more than 4 categories, no order. So you might just using this coding to get the multi-normal logistic regression. And so you need to specify link function is G logit, which specifies a generalized multi-normal logit. And the output will give separate parameter estimates for each comparison. So here is 3 logits, right? So you using others as the reference group. So you have a STEM versus logits. STEM versus others, 1 logit model. Second logit model, medicine versus other. The third is law versus other. So you have 3 logit models. Okay, this is model for multi-normal logistic regression model. Now let's looking at more interesting case is ordinal logistic regression. This is probably more common than nominal model, nominal response. Ordinal logistic regression is used for response outcome with more than 2 categories that are ordered. So this is called ordinal responses with ordering. For illustration, let's say we have C order categories, 1 to C. That's so 1 to 3. That's no meaning, just the meaning. This is order. This is order. For example, disease severity have a normal, mild, moderate, severe, general health condition, poor, fair, good. Right? This is the ordinal responses. So I don't want to note this again. This is 1, 2, 3 is not the value. It's just that when you have coded your Y coded 1, 2, 3 in the SAS or R syntax. Once you have this Y as a response variable, you ask the software to fit an ordinal response variable, ordinal regression model. They will consider this as order category, not real numbers. It's order categories. So we know ordering contains information. So when you have order, you're treating ordinal outcomes as nominal will be inefficient because you lose information. The other is, we just said that if you fit ordinal outcomes, you're treating ordinal outcomes as nominal, you have a lot of parameters because you're using multinomial regression model. We have lots of regression coefficients to be estimated. So this is another meaning of inefficient. On the other hand, if you're treating ordinal outcomes as continuous, this may not be appropriate. So may violate model assumption. So we need different methods for analyzing ordinal responses. One common model is using cumulative logit models. So this is the one common model, the most common model. So this is, I'm going to using the rest of this lecture time to focus on cumulative logit models. How we use this model to analyze ordinal outcomes. So the key concept is cumulative logits. So let's illustrate this cumulative logits in this context. Is suppose, okay, we have y is ordinal with all the categories from 1 to c. Again, this is number no meaning, just mean I have all the categories. I have c categories. And we define the cumulative probability of being at or below category J is this. So this is a cumulative probability of outcome response being at and below category J. This is just a sum of probability of being in each category below J. Right? So let's say probability of at or below category 3 is just the probability of being category 1 plus probability of being category 2 and plus probability of being category 3. So this is adding together, we call the cumulative probability. And we define this cumulative probability, they have C minus 1. There are C minus 1 cumulative probability with index J. So the first cumulative probability is less than equal 1. Second is less than equal 2. All the way to less than equal C minus 1. So you have C minus 1 cumulative probabilities. We don't need the last one because once we have cumulative probability being or at below category C minus 1, we already know the last one, which is 1 minus this cumulative probability. So how we define cumulative logit? Cumulative logit is defined as log odds of cumulative probabilities. So log odds of what? Odds of cumulative probability of being or at or below category J to the probability of 1 minus this. So the probability of being above category J. So this is the log odds. This is the log odds based on cumulative probability we call the cumulative logit. So this is may be more clear, right? This log odds. What's odds? Is from first, the numerator is pi 1 pi to pi all the way to pi j. Is the probability being category 1 plus probability of category 2 all the way to the j. And the denominator, okay, denominator is probability of j plus 1 to probability the last one. So you can think about this is j is like an index, right? Index, moving index. Once you have split the data, let's say j equals 3, so you split the data as equal or less than 3. versus greater than 3. So you can have C minus 1 cumulative logits. So let's looking at the example. This may be more clear. Is let's look at the pen scale. Pen scale is Y. The first category is none or very little pain. Second category is troublesome. The third category is severe. Say I have 100 people sample, and among these 100 people, 20 responded as 1. 20 responded having no, none, or very little pain. And 30 subjects responded troublesome, and 50 responded severe pain. So what is probability of being category 1? 20%, 20 out of 100. Probability of being at category 2 is 30%. It's 30 out of 100. And the last one is 50 out of 100. Now we can calculate cumulative logit. Cumulative logit less than equal 1. This is just a log odds. Log odds of what? Log odds of this probability to the rest. Right? The probability of being 1, that's 20%. The ratio of 20% to summation of sum of these two categories, that's 80%. The second logit, less than equal 2. This is combine these two categories, which is combine these two. So it's like this, right? Divided by the last one. The last one is 50%. So this defines with 3 categories, with 3 pain categories, we just need to estimate 2 logits. 2 logits, right? Now, this is different from the previous nominal model. Nominal model different. Nominal model is because of no ordering, is each category compared to the last one. So each category 1 compared to the last one, category 2 compared to last one, because there's no ordering. Here there is ordering. So we actually take advantage of this ordering. We combine the first logit, just 1, versus combination of 2 to C. The second logit is combine 1 to 2 together to combination of 3 to C. So this is take advantage of ordering. Now we have a model. What is cumulative logit model? Cumulative logit model is use all these cumulative logits simultaneously. So now we have this model form. So we have this model is J. How many logits? We have C minus 1 logits. We use this C minus 1 logits simultaneously. We let this logit equal to intercept plus regression coefficient covariate. And so here I would just say is for simplicity is index I that tracks subject I is not shown. So you can think about this actually Y sub I. So Y sub I denote for the response in subject I. So Y sub I less than J equal to this also have X sub I. Right? So I just is for simplicity, so index I is not shown. Now, let's look at this model carefully. So what this model says is that each cumulative logit, which is J from 1 to C minus 1, has its own intercept, denoted alpha J. So you think about have alpha 1 to alpha 1 for the first logit, alpha 2 for the second logit. So each logit, cumulative logit, has its own intercept. So how many cumulative logits? C minus 1, meaning I have C minus 1 intercepts. And also, note that these intercepts are increasing in J. So as J increase, this value is increase, model 2 increase. This is go back to here. So this probability, cumulative probability increasing as J. Because the J equal 1 is probability of Y equal 1. J equal 2 is combined, is 1 plus 2. So the numerator increase, the denominator decrease. So this value is increasing function. Model will increase in J. What does that mean? Is alpha J increasing. Alpha J is always increasing, is increasing in J. Right? However, you see beta. The model restricts beta to be the same for all cumulative logits. So beta is the same. Beta estimated to be the same across cumulative logits. And this resulted in the proportional has a proportional odds assumption. So I will talk this in next slide. So let's just summarize this model. This model is said is I have C minus 1 cumulative logits. And each logit, so J from 1 to C minus 1, each logit has its own intercept. However, the beta regression coefficients for covariates are the same across the cumulative logits. So what does that mean is X covariate has the same effect, have the same association with logit with this logit, regardless of whatever cut points you are using. That's just what they said. So with this restriction to the same beta resulting in the proportional odds assumption. So let's talk about this. What does that really mean? So proportional odds assumption mean is, so let's still consider Y is ordinal with all the categories. And there is a total of C minus 1 cumulative logits. Now, for example, you can write this model down as the first logit is Y less than 1, less than equal 1, have alpha 1 is its intercept, and the beta, you can see the X can be understood as age, right? Age. Then you have second logit, then beta alpha 2, same beta. Then the C minus the last logit is alpha C minus 1, is still you have same beta. That's is because the model, that's the model form. What does that mean is this mean is logit. All this logit line is parallel. This is the logit for 1 compared to greater than or equal to. There's a 1, the first logit is 1 compared to combination of 2 to C. This is the first logit. Second logit is 1 and 2 combined compared to 3 all the way to C. So you have this C minus 1 logit, cumulative logit lines. They are parallel because you have same beta. Slope are the same across these logits. They are different in intercepts. The first logit is alpha 1, second logit is alpha 2. What does this say is the cumulative logits are parallel across cut points of categories. The odds ratio for X is the same across cumulative logits. This also equivalent saying is the effect of explanatory variables does not depending on response categories. And this model is often called proportional odds model. So this is what this said, that is because these logit profiles, logit lines are parallel and proportion, right? So same proportion across logits. So this model is commonly called proportional odds model. Okay, so let's just summarize how many regression parameters in the model. C minus 1 intercepts and P number of slope if you have P independent variables. Right? So let's look at the D. So alpha, J from 1 to C minus 1. So you have C minus 1 intercepts plus whatever many of covariates you have. If you have a P covariates, then P parameters. So the number of parameter to be estimated is C minus 1 plus P. Now you can see this is the model, the regression curves are, the number of parameters to be estimated are greatly reduced from previous nominal model. Nominal model, you have C minus 1 intercepts plus each logit have different coefficients. Here the ordinal model is the regression curves are the same across the logit. So you only just estimate the P slope coefficients. The interpretation is very similar. So this is just for example, beta is just the log cumulative odds of being at or below category J for each 1 unit increase in X. And this is just the cumulative odds ratio. And if X is categorical variable, then this is just e to the beta is just the cumulative odds ratio of being at or below category J for female versus male, for example. So it's, if the X is represents sex. Okay, so I'm almost there. So let's just looking at the example. So example is back pain ratings from 180 women who gave birth at London hospital. And the outcome has 3 categories from none or very little pain to troublesome to severe. And let's consider just the one covariate, which is age. So the research question is, does age explain the degree of back pain experienced among women who gave birth? And we can fit a cumulative logit model. So in this model, there are C equal 3 categories, meaning that we need to estimate 2 cumulative logits, right? The first logit is y less than equal 1. The second is y less than equal 2. So the cumulative logits, first is less than equal 1. Second is combine 1 and 2. Now here, I put the I there. Right? This is y sub I index the response from subject I. So these are the results. Logit, the cumulative logit, this is the logit of cumulative probability is just the log odds of cumulative probability of less than equal 1 to greater than 1. So 1 less than 1, greater than 1, meaning 2 and 3. And this is the model output. Is alpha 1 is this alpha 1, and beta, this is for the age effect. And the second logit is less than equal, cumulative less than equal 2. This is less than equal 2 compared to greater than 2. Then I have alpha 2 and also age. So this is, you can see that the intercept, right? Separate intercepts for logits, but beta is the same regardless which logits. So basically the pull data from different logits into the same parameter, beta. Let's look at the detail about how we explain this data, right? For the first logit, this logit is for responses 1 versus 2 and 3. So odds ratio for age is just e to this parameter, right? This parameter, this is the value. And this is meaning that for each 1 year older, the odds of experiencing none or little pain decreases by 5%. And for the second logit is this. So these responses 1 and 2, 1 or 2 versus 3. So the odds ratio for age is still the same here. And for each 1-year-old, the odds ratio is the same, but the explanation is different, right? Because I'm looking at this odds. So this is odds of experiencing none, little pain, or troublesome. So basically combine 1 and 2. Decreases by 5%. So you can see that age has the same odds ratio across the two logits. Age effect does not depend on the cut points used to categorize the outcome response. Now, clearly, you see that this is quite a strong assumption, this proportional odds. You see that? So this means age effect is the same for the odds of experiencing none compared to troublesome and severe. The second is odds of 1 and 2 combined compared to the 3 severe. So the age effect are the same for these two odds, for these two logits. So this is quite a strong assumption. So talk about last we talked about let's talk about the prediction. Almost there, okay? So talk about the prediction. Find the predicted probabilities. Find the predicted probabilities is recall we can use inverse logit link. This is covered by lecture 1. Is under logistic regression model. You use the inverse logit link to find the probability. The probability is just a function of the numerator is this is the linear predictor eta. This is the linear, so e to the eta divided by 1 plus e to the eta. Say, suppose we are interested in age at 20 years old. So let's find the first logit. So first logit is just plug in this number. Let's go back to this. Is this? So you plug in age 20 to this model, you find the inverse probability, inverse logit link. Right? So you plug into, so this is the eta, the linear predictor. So you get 59%. Right? So for the people at 20, the probability of experiencing no pain or little pain is around 60%. The probability. So this is the little or no pain. Let's find what about the probability of second category, which is probability of experiencing troublesome at age 20. So in order to find y equal to, so let's break down y equal to is less than equal to, less than or equal to minus less than or equal to 1. Right? So this one less than or equal to is this one. You need to use the second one, second equation with same beta but a different intercept. Okay, so that's this one minus this one. So you can see the beta is the same, but the intercept are different because each one associated with different logit. Then, so you can do this, then you get 29%. So the probability of experiencing troublesome for age at 20 years old is around 29%. Okay, so let's talk about what, when, When is proportional odds assumption likely violated? So first of all, you always need to guided by the knowledge, guided by the literature. For example, if you think the predictors effects differ by cut points of all the categories, for example, if you have a hypothesis there is a strong effect for mild versus benign, but a weaker effect for severe versus moderate, clearly in this case, proportional odds assumption is violated. The second approach is, so you should not use this model. You should not use this model. Another way of doing is you can perform a statistical test for the proportional odds assumption. So under this test, the null hypothesis is that the assumption is valid. And if you see the lower p-value, you would reject the null hypothesis, then concluding that the assumption may not be valid. And however, we know that so in the SAS guide cautious that the test may reject more often than it should, especially if the sample size is large. This is not surprising, right? Because when the sample size is large, it's more likely to get small p-value, then lead to reject the null hypothesis. So it should be cautious when you're using statistical test for this proportional odds assumption. Right? Because if the sample size is large, you're more likely to get a small p-value. And so you should guided by knowledge, guided by the hypothesis, the purpose of your study. Let's say the purpose of your study. Okay. So we talk about this cumulative logit model, which is a proportional odds model. This is a common model. Of course, this is a common model, not the only model. You need to consider alternative methods. Sometimes you may need to consider alternative methods, especially when the proportional odds assumption may be violated. And there are some alternative methods, for example, partial proportional odds model. Or you can go to the multinomial logistic regression, which is ignoring ordering. Now we know that this requires large sample size. So there are some options there, and you can also like a combine, right? So the combine categories, that's another way of doing combine categories. Okay, so lastly, how we fit this model. And just the example here, the pen level, so back to the previous example, pen level coded the 1, 2, 3. So here is, again, 1, 2, 3 has no meaning, just the mean, this is all the categories. So once you put you're using prog-logistic model, prog-logistic procedure, you specify pen level as the outcome. Once you have this, you say, I want a cumulative logit. Once you say link function is cumulative logit, this will automatically consider, SAS will consider this is ordered category outcomes. So it will use cumulative logit as the method we just described. All right. And you can also using prog-gen mode. Using prog-gen mode, you need to specify distribution is multinomial, and the link function is cumulative logit. That's the SAS procedure. And our package is you will need to use another package, another function. So we talk about this more detail on Thursday, and you will have exercise to use SAS and R to do some exercise problem. And I think that's all. And please go through this recording. You may need several times to go through this, and these are the complicated concepts. So okay, this is all for today.